Hello, welcome to Advanced Composites. Today is the fourth day of this course, and today we will continue our discussion on failure in composite materials, specifically at the ply level. And what we have discussed till so far are three different failure theories which help us understand whether a composite ply will fail. And these three theories are maximum stress theory, maximum strain theory, and maximum work theory. In this context, it is important to understand how the sign of shear stresses influences the failure of a composite. So, this is what we plan to discuss today, but before we do that, we should have a very clear understanding as to what our sign conventions are. So, sign conventions. So, if I have a composite material, I can subject it to tensile stress, and in that case sigma L is positive. Okay. I can subject it to tensile stress in the transverse direction, sigma T. So, this is the direction of the fiber, and I can also subject it to shear stresses, and this is one way I can specify the shear stress. So, this is tau LT, and in this case tau LT is positive. This is our sign convention. Okay. What would be the case of a negative shear stress? In case of negative shear stress, it will be placed like this. Oh, before that I wanted to, we should specify what our axis system is. So, this is a positive convention, as this is positive x and this is positive y. Okay. Similarly, if this is positive x, this is positive y, then this is tau x, tau LT, and tau LT is negative. Tau LT is negative. So, now let us move on and let us understand what happens when the direction of shear stress it gets reversed. So, we will consider two cases. Case 1, fibers are aligned to loading direction. Fibers are aligned to the loading direction, and here in case 1 we will have two different cases. So, this is case 1 A, fibers are aligned to the loading direction. So, these are the direction in which fibers are running, and this is the case of a positive shear stress, and this is my axis system. This is the case of, this is the axis system. So, this is case A, and then B, we apply a negative shear stress, fibers are still aligned to the loading direction. So, this is my x axis, this is the y axis, but here I am applying negative shear stress. Okay. In these cases, So, when fibers are aligned to the loading direction, then in this situation the direction of shear does not matter. It really does not matter, direction of shear. Okay. And you can see that mathematically. So, if this is tau LT and this is tau LT, you can see that mathematically, because if you plug this, in this case you plug tau LT into this equation, all these terms will be 0, because there is no sigma L, there is no sigma T, there is no sigma T, only tau LT is there, and whether tau LT is positive or negative, it does not matter, everything gets squared. So, the failure criteria does not change. So, direction of shear stress does not matter in case 1 when fibers are aligned to the loading direction. Okay. The second case is when fibers are not aligned to loading direction. Fibers are not aligned to loading direction. If fibers are not aligned to loading direction, then what does it mean? So, we will draw a picture. So, these are two cases, and fibers are in this case running like this. So, the angle is, let us say, positive theta, and in the second case also fibers are running in the same direction. So, here also the orientation of fibers is at positive theta with respect to the x axis. This is my x axis, y axis, y axis. But the difference in these two cases is that in one case I have a positive shear So, this is tau LT, and in the other case I have negative shear. In this case, the direction of shear, whether it is positive or negative, it will matter significantly. Now, in this case, if we have to predict the failure of the composite, we can excuse me, sorry. So, this I should not call it tau LT, I should call it tau XY. Why should I call it tau XY? Because I am applying tau with respect to x and y direction. In the other case, the L direction and the x direction, they were same. So, tau XY was same as tau LT, but in this case I have to do, I call it tau XY, right. So, here tau XY is positive and here tau XY is negative based on our convention. Now, if we have to predict failure in this case, what do I have to do? From XY plane, I have to go to LT plane. I have to compute stresses in the LT plane. Right now, in the XY plane, sigma x is 0, sigma y is 0 and tau XY is not 0. But for computing failure, I have to first go to LT plane. So, I have to compute sigma L, sigma T and tau LT. Okay. And let us assume that this theta in both the cases is 45 degrees. That makes our things simpler. So, if that is the case, so if I go from this XY plane to LT plane, what happens in the first case? The fibers are oriented like this, and if I do the computation, I will find that there is a compressive stress in the transverse direction. So, sigma T is compressive and longitudinal stress is tensile. when I do the calculation in terms of tau xy. In the second case, fibers are still in this direction, the situation changes. Here sigma L becomes compressive and the transverse stress becomes tensile. Now, clearly the second case, the composite will fail early because the composite is extremely weak in the transverse tensile direction. If you subject a composite to tensile forces in the transverse direction, it fails at a very early stage. So, this is much weaker relative to the first case. So, the overall point is that if the fibers are aligned to the loading direction, that is if the LT plane and XY plane are aligned to each other, then the direction of sign does not matter. But if the LT plane and the XY plane are not identical, if the axis system of LT axis system and XY axis system are not identical, then the direction of sign makes a very significant difference. So, this is something we will also do through an example. So, we will do this through an example. We will do this through an example. So, we have a material where the fibers are oriented like this, okay, and this is my x axis, this is my y axis. So, this theta we say is 45 degrees, theta is 45 degrees, okay. And so, this is a single layer and the strengths of this material are 500 MPa, sigma Lu prime is 350 MPa, sigma Tu is 5 MPa and sigma Tu prime is 75 MPa and tau LTU is 35 MPa. So, this is given. And then the question is, at what value of tau xy will composite fail? If, and there are two conditions, A, tau xy is positive and B, tau xy is negative. So, these are the two conditions, okay. So, at what value of tau xy will the composite fail? If tau xy is positive, and the other one is if the shear is negative. So, we make a table. So, whether it is positive or negative, we have to calculate sigma L, and sigma L is tau xy sin 2 theta, sigma T is minus tau xy sin 2 theta and tau LT is tau xy cos 2 theta, and we will make this table. So, in the first case it is positive shear and in the second case it is negative shear. So, theta is 45 degrees, right. The only thing varies is whether tau xy is plus or negative, that is all. Okay. So, this is plus tau xy, this will be minus tau xy, and this will be 0, and in the other case this is minus tau xy, this is plus tau xy, and this is still 0. So, for these two situations now we explore the failure stress. So, positive shear, and what do? We use the maximum work criteria. So, what is it? What does it say? It is sigma L over sigma Lu whole square minus sigma L by sigma Lu, sigma T by sigma Lu plus sigma T by sigma Tu whole square plus tau Lt by tau Ltu whole square at. So, when it is failing, when the composite fails, this becomes 1. So, for condition for failure is this is equal to 1. So, we put in these values. So, when it is positive shear, then it is tau xy divided by what? Sigma L is positive, sigma L is positive. So, sigma Lu is, what is the value of sigma Lu? 500, right, and this whole thing is square minus tau xy by 500 times tau sigma T. Now, sigma T is negative, sigma T is negative, this number is negative, right. So, it means it is compressive, its value is still tau xy. So, tau xy, and then the corresponding strength is 350, right, 350 plus sigma T, which is again tau xy divided by sigma Tu, which is, and this is again compressive. So, 75 plus 0. Okay. So, this, if you solve for tau xy, you get tau xy fail, at which it will fail. This comes out to be 75.4 MPa using this thing. And if we are talking about negative shear, then the numbers change. So, this is how the equation looks like: tau xy by 350 minus tau xy square by 500 into 350 plus tau xy by 5 square plus 0 is equal to 1, and this gives us a tau xy fail is equal to 5 MPa. So, there is a very significant difference between the failure strength of the material if I have a positive shear or a negative shear. So, this is what I wanted to illustrate in this example, and we will close this discussion today, and tomorrow we will start discussing failure of the laminate, because till so far we have only discussed how a particular layer fails. Now, we will start discussing about failure of the laminate. So, that is pretty much it for today, and we look forward to seeing you tomorrow. Thank you.